Hello, this video is going to take a quick look, at least hopefully a quick look, at the two different ways we've modeled energy. All right, these are the energy pie charts, and we'll take a look at those. And then the energy storage model we had are the LOL or energy bar charts. And what I want to do is just kind of compare and contrast these two methods of diagramming out or modeling out some energy interactions, right? And I will take a look at just one in particular. We're going to take a look at the one that was labeled as example number 1 on this worksheet. This is from a video that's called Open or Closed System. If you haven't watched that yet, you will absolutely need to do that to be able to be successful for learning target A. That is a part of what you have to decide with the system. Is it open or closed before you can actually pick the correct model for how that's going to work. And we'll just kind of cover that as we go through this. So to begin with, actually let me just put this up here, right? So we're looking at a ball that is kicked once across the floor, and eventually it rolls to a stop. So we're not doing the example at the top, we're doing this example right here. A ball is kicked once across the floor and eventually rolls to a stop. So for these energy pie charts, what we do is we do need to label above the pie chart kind of the portion, the part, the section, however you want to call it, of the interaction we are looking at. So if we're looking at this one, again, I'm going to have to maybe write kind of small. I could maybe zoom in just a little bit, but I do want you to be able to see all of the actual pie charts here. I don't know how many we'll actually use with this example either. We'll just kind of see how it makes sense as we go across. For most problems, I will tell you, using 3, using 4 pie charts, but after that, you can kind of decide which part of the interaction you want each one to represent. For here, we're going to look at as it is kicked. So this means it's being kicked. It really hasn't moved a lot yet, but it is being kicked. And this is right after it is kicked. So this is right after the kick. All right, this is maybe halfway across the floor. Sorry, I didn't really leave enough margin. I could write well here. And then this one, let's just say this one is stopped. So we'll do these 4 kind of parts of the interaction. We won't use the last one. So as it is kicked, oh, actually, let me back up one more step. When we're doing these, and I didn't really leave enough room to do it there, so I'll write up here. What we also need to do is write the system. And here's the thing. If we're using energy pie charts like this, the system must be closed. Once again, a closed system has no energy flowing in or out of the system. Throughout all 4 of these parts of the interaction, all of the energy has to be inside or stored in one of those objects in one of the storage forms that we have. So, right, there is no energy going in or out. I mean, I suppose theoretically, if we would have energy going in, we could make the circle bigger, or energy going out, the pie chart being smaller, but that is just too hard to judge. So our general rule of thumb is for these energy pie charts, the system has to be closed. And if we're kicking a ball and having to go across the floor, kind of the minimum number of objects in the system we can have so it would be closed would be the person and the ball. Excuse me, because that first interaction is what moves the ball. And then the ball and the floor, because the floor is going to be what changes the energy storage type into eventually thermal energy for part of it if the ball is going to stop. So those are our 3 objects in the system. Some people would like to add the earth because the earth is actually holding the ball to the floor, and I suppose you could possibly do that, but really what we're looking at with energy again is what changes. And when we say earth, we're more looking at the gravitationally stored energy that the earth is giving an object because of gravity, and in this case the gravitationally stored energy is not changing, assuming the floor is level anyhow, or the ground. Oh, this did say floor in the problem, so there we go. So as it is kicked, right, the energy is actually residing in the person, and the person has chemically stored energy. Now this also depends upon which part of the kick we are looking at, because as you kick a ball, right? Part of that energy is going into elastic energy to begin with, and it squashes the ball. So if you wanted to take part of this and say it's elastic energy too, you can do that. But I'm just saying, as it's kicked, that you've kind of cocked your foot back. Your foot is coming forward and getting ready to kick the ball, and that's all coming from the chemical energy inside of your body. Right after your kick, or excuse me, right after the kick, part of that chemically stored energy has been changed into kinetic energy, because the ball is now moving. Now, what a lot of people have done is going through problems like this, the chemical energy just disappears in these diagrams, and it cannot. If you're making a person part of the system, the energy in that person, the energy remaining in that person, has to be in each one of these energy pie charts. The energy in the ball, stored in the ball in some storage form or the other, has to be in each of these pie charts. The energy in the floor has to be in each one of these pie charts. Right, so again, if the ball is just sitting there on the floor, the only object that really has energy is the person, and that's chemical. Right after the kick, the ball is now moving and has kinetic energy, but the person is still there. So they still have chemical energy. Now, realistically, if you add up all of the chemical energy in all of the cells of your body, right, the amount of that changed into kinetic energy with a single click is probably a really tiny sliver. But we're going to make it big enough that we can actually see how this energy is possibly interacting and being stored in some different forms as we move through the problem. So I definitely wouldn't probably even make it half and half either, but make it big enough so that we can do some things and see how this kinetically stored energy is possibly being stored in some other ways throughout the problem, but don't make it too large to make it unrealistic either. So that is the thing. If the person is standing and watching this ball, the rest of its motion, right, the amount of chemical energy in their body is not changing. So what I'm going to do, and it doesn't look like I quite made it, I want all of these parts to be the same, because the chemical energy inside of the person is remaining the same throughout the rest of this interaction. What is changing is the kinetically stored energy inside of the ball. It has the most kinetic energy right after it is kicked. And I don't know if it's halfway across, but what I'm looking for is that point where maybe half of the kinetic energy is still kinetically stored energy, is making the ball move. The question is, what happened to the rest of that kinetically stored energy? And what happens is the floor, through some friction, is changing that energy type into thermal energy. Right? And thermal energy for these diagrams, rather than labeling it ETH, it's better if we just black it out. Because once again, once energy becomes thermally stored, it really cannot change storage types back into something else. Chemically stored energy can become kinetic. Theoretically, I imagine kinetically stored energy could become chemical. If we're doing something to say, charge a battery, we probably can't really add chemical energy into a person, but we can do the chemically stored energy inside of a battery from kinetic. Unfortunately, we're not going to get to do that, since we can't do our electromagnetism unit this year, but that is definitely possible. Once energy is changed into the storage type of thermal energy, though, that is where it's going to remain. In fact, once the ball is stopped, all of the energy that was kinetically stored when the ball first started moving has now transformed into thermally stored energy, and the ball stops. Because once again, once the energy has been transformed into thermally stored energy, it cannot be transformed back into one of the other energy storage types. So, for example number 1, on this other worksheet, right, where a ball is kicked once across the floor and eventually it rolls to a stop, with the person, the ball, and the floor being the closed system, this is what the energy pie charts would look like. All right. Now let's take a look at the LOL or the energy bar chart model. This one is a little bit more usable, I think, in some cases, because this doesn't have to be just for closed systems. It could be closed or open. So we're going to do this both ways. We're going to do one set for the closed system and one set for the open system, right, for this same example. So once again, the example we're going to use is the ball is kicked once across the floor and eventually rolls to a stop. Now, as we're going through these, what some people are doing, since these are circles, right, are they trying to do the energy pie charts in between? No, what this circle does is the circle represents the system, right? It represents all of the objects in the system that are interacting with these energy storage types. So if this is a closed system, once again, we need the person, the ball, and the floor. And the person, ball, floor. So once again, however many of these O's there are in our LOL diagrams or in our energy bar charts, I'm just going to start calling them energy bar charts, I think, instead of giving you both options, right? For a problem, each one of these should have the same objects in the system. Right? We're not going to change the system in between one of these diagrams and the other. For the open system, we said this was just the ball on the floor. And I tell you what, rather than going back and forth, this is the only time right now I'm going to go from one to the other just to make that distinction. Otherwise, we're going to do this problem completely, and then we'll do some comparisons back and forth. But this is why it really, at the very beginning, you have to decide what your system is going to be. Because if the system is closed, these diagrams are going to look one way. If the system is open, they're going to look somewhat similar, but there's going to be some pretty significant differences also. So that is the first decision you need to make when you're trying to model things. Once again, if you're choosing an open system, or excuse me, if you're choosing a closed system, what you do have is the option of, are you going to do the bar charts or the pie charts? You can use either one. Right? If the system is open, you absolutely have to use these energy bar charts to describe things. I apologize, I should have had this written out ahead of time. I didn't, so let me just take one other quick moment. What we do need to do is take a look at the kind of energy types, storage types we're going to have. In this problem, we decided we're going to have chemical and kinetic. I'm going to kind of go back and take a look at these pie charts for a minute. We had chemical, kinetic, and thermal. Those were the three altogether, and then we're going to label this. So this is ECH, EK, and ETH. It's best practice to label all of your bar charts in the same order, because that way, as others are looking at your diagram and we're kind of looking at how these bars are going to interact, it doesn't make much sense to have the first bar here be chemical, the first bar here be thermal, and the first bar here be kinetic, because then we can't really see the energy interchange quite as easily in the energy interactions. So we need all of the different types of energy involved in the interaction across the bottom, written in the same order. Which order they're in, again, doesn't matter, as long as they're written in the same order all the way across your diagram. So for this closed system, I am going to make a few comparisons kind of back and forth between this and the pie chart. Right? We said to begin with, all of it is chemical, and there's some chemical and kinetic, and the chemical, kinetic, and thermal, and then chemical and thermal. Right? So what we need is a set of bars that represents how much energy there is. You know, once again, just like I didn't really necessarily make a conscious choice at how big of chunks these pie charts are, we don't necessarily need to decide exactly how many bars there are up here either, but we need enough that we can separate them. Especially this diagram in the middle is kind of the most complicated one with three different forms of energy. We need to start with enough bars of energy that we can kind of divide it amongst these three energy storage types and have a number that makes sense, possibly. Right? So, just start maybe with 8, right, of chemical energy. And so what we're going to do is we're going to draw a big bar, and it's going to have 8 subsections in it. And once again, it would be helpful if you would, right? The video, that 8 doesn't even show up very well, right? Actually, just label how many are there if there's a significant number. If there's over, say, 3 or 4, so that way it's easier for me to see exactly how many are there. And if we do start out with 8 bars of chemical energy, and this is a closed system, right, we need to have 8 total bars of energy at this interaction and 8 total bars of energy in this interaction, which, by the way, I did skip an important part of this also. So on this, we labeled each of the energy pie charts with the part of the interaction we're looking at. For this, we label the diagrams. We don't label the circles. Once again, the circles are our system. We label the diagrams. So this first one is as it is kicked. Right, and I've only got 3 here instead of the 5, so let's just do, we'll do halfway across. Excuse me, halfway across. And then we'll do, well, I'm having a hard time writing today. They're supposed to say the word across. Trust me, it says across. And we'll do stopped. All right. So if it's halfway across, we still have some chemical energy because once again, we are still here. And again, you can choose a number that makes sense to you. All right, I might just choose 6 for this. And then we had some kinetically stored energy and we had some thermal energy. So 6, 1, and 1, that is still 8. All right, once the ball is stopped, we still have the chemical energy in the person, which is still 6. But now the rest of the energy is thermally stored. So it might look something like that. Once again, when I'm looking at these, I'm not really particularly looking at exactly how many bars there are, but I'm looking at what happens, right? And throughout this interaction, the chemical energy of the person is going to go down somewhat because part of their chemically stored energy went into the ball to make it move initially. As we go from starting to halfway across to stop, the kinetic energy is going to get less, and it does. And the reason the ball stops is because that kinetically stored energy is going to be turned into thermal energy. So the thermally stored energy should be getting larger. So as long as that works, your diagram is correct. All right, let's take a look at the open system. So once again, I want to take a look at the same 3 spots. So it's as it is kicked. So your leg is in motion, getting ready. Your toes just getting ready or the side of your foot, depending upon how you're kicking it. They're just getting ready to hit the ball. We'll look at the ball going halfway across the floor. See if I can write across appropriately this time. That looks better. And then once again, we'll look at stopped. So if this is an open system, right, the person is not part of the system. Right, so there will be no chemical energy here now in this diagram because the person is not part of the system. There will be no chemical energy in the ball or in the ball floor system once it's stopped because there is no energy in the system, or the person is not part of the system. So there is no person here anywhere. So there is no chemical energy that we're going to put on this diagram anywhere in terms of the bars of energy anyhow. So the only energies we're going to have here will be kinetically stored anyhow, and thermally stored. So there we go, looks something like that. So if we go back up to our top diagram, right? We had that chemical energy in there because the person was part of the system. In this case, we are not. So initially when we start, if we're looking at just the ball on the floor and your foot's coming forward, but the ball is just sitting there and your foot's coming forward and the ball is sitting there, there is no energy in just the ball on the floor by itself. Now, once again, it depends upon how many bars you want to put. I guess if I want to be consistent, right, I will put the same number of bars of energy here I had in the top example, and then you'll see why when we go back and we kind of put this back together. Right, halfway across, we have some kinetically stored energy and some thermally stored energy. Once it's stopped, it's all thermally stored. There we go. So it's a lot different diagram because the person is not part of the system. So the energy that remained inside of the person is not on our diagram at all. If we do go back up and look at the top one, right, we had 8 bars of energy and chemical to begin with. Here the person still had 6. So the part of the energy that kind of left the person in chemically stored energy that was transformed into kinetic and thermal energy were just these 2 bars. So really there were just 2 bars of energy that were transformed into the ball on the floor. So that's why there's only 2 bars of energy here. But those 2 bars of energy came from the person, and the person is outside of the system. So with an open system, you have to somehow diagram that happened. So what I'm going to do is I'm going to put an arrow going in with some energy bars, and I'm going to have 2 bars. There are 2 bars of energy there. Sorry, my cutoff between the 2 is kind of right on the edge of the circle. Once again, if it's not clear, you can always just kind of write a number off to the side so it's clear what's going on. So this is the 2 bars of energy coming from the person. It was chemical energy that the person is putting into the system. You could label that chemical energy. What I'm more interested in is how much energy there was. And so this represents the 2 bars of energy that is leaving the person, right, and being transformed into kinetic. Initially, it's all kinetic energy in the ball, right? And then halfway across, it's kinetic and thermal. And then those 2 bars at the end are all thermally stored energy once the ball has become completely stopped. So that's how we diagram an open system. If there's energy from some other object going into the system, we diagram it in. If there's examples, and we'll work through a few of those in another video, I'm sure, where energy is leaving the system, then we do an arrow going out with the amount of the amount of energy that is leaving the system. So we have 2 different ways of diagramming energy. Right? We have the energy pie charts. We can only use those for a closed system. And we have the energy bar charts, which we can use for a closed system or an open system. It depends upon how it goes. These are only for a closed system. Let's go with the energy pie charts, closed or open with the bar charts. And it just depends upon how you want to diagram the energy. And if I give you an interaction but don't specifically say which type of system you want, you can either make it open or closed, and that will determine which type of diagram you're going to show me. Thanks for watching.